Hi everybody, I would like to discuss about new types of problems. We apply here sigma equals epsilon, so-called Hooke's ratio. In this example, let's think about how it works. Firstly, in the laboratory, we have this kind of one frequently. In the laboratory table, laboratory bench, we have this kind of device, okay. On the basement, on the top of basement, there is some structure, this structure, BC, this structure, and it's fixed to basement, and we have A, L type, this type component, which is fixed to B point, point B, pivot point. It can be freely rotated around here, around pivot point B, and at the same time it is connected to spring, and finally bolt and nut, thread rod and knuckled nut, bolt and nut is attached here, and it is also connected, all is connected, and at the end of the A we have some places to put some weight on it. Principle is like this one. When you increase the weight, then the position is changed somewhat. Of course, we have some constraint in spring, but when you increase this weight, then we have some limitation of a spring constant. Then this point is moving right side. It can be moved to right side. This position is moved to right side. Then when you rotate this nut, then moved position can be go back to original place. We can adjust it by applying nut, by operating nut, by rotating nut. Then we can move to original place. This is the total operating mechanism. Okay, our question is like this one. When you add some weight, how many revolutions is required to go back to original position? That's our question here. In order to solve to this problem, we first understand some concepts related to pitch. Pitch of a thread is, let's say, P is what? When you rotate one revolution, when you rotate one turn, then the movement of thread is pitch. Okay. When you move here delta, when delta moved, then how many rotates is required? When you rotate some pitch, if it is divided by pitch, then you can have how many rotation is required. Okay, that's the relationship for bolts and nuts and movement. Okay, next the spring constant. When you introduce some spring constant is like this one. Spring constant, maybe external force is P and movement is delta, and we have this kind of relationship. This one is, I've already told you, Hooke's law. There is some linear relationship between external force and displacement. Okay, now let's think about this component. When external force is acting like this one, W, then if you draw a free body diagram, what's the free body diagram? Something is isolated. Then we can think of imaginary force acting isolation point, isolation area. Okay, external force is W, and A, B, C is also given. And by spring constant, springs, we introduce f, this kind of value. Okay, here rotation is free, that's why there is no constraint around rotational movement. If it is not rotational free, then we introduce some kind of moment is acting at this point, but in this case it's free rotation, that's why there is no constraint around rotational movement. Okay, now we draw this kind of free body diagram. Then our goal is to find f. Why we find f? Because we have some relationship, f equals k delta, spring constant k and delta. If we calculate if we know delta value, then we can have n revolution. Okay, anyway, to find f is very important, that's why we introduced f. Okay, at this point, vertical and horizontal direction, in both directions we have some imaginary forces are acting like this one for free body diagram. Now let's think about this one. Normally, as when you already know some kind of direction, let's say imaginary x and y direction, and sigma f equals 0. Normally I do like this one, x direction is positive, then this f and f is 0, deleted, nothing happens. And y direction, this direction, y direction, let's say this one is x, fy equals 0, then minus w plus w is 0. Okay, nothing happens. This one is automatically f and this one is w, because there is not any other. Next one, let's think about moment around B point. Let's say moment B point equals 0, because it's in the state of equilibrium. We consider around this position. Let's say counterclockwise direction is positive, then we can say W and B is positive, and FC minus FC. Okay, then we can calculate what f equals B over C W. Okay, we've calculated the f value like this one, and f is substitute here in this equation, then we can get delta. We know delta, and we know the pitch is given like that. Then finally you can find revolution. How many revolution is required to place back to original position? Okay, I repeat these cases again, this example again. In this example, it is in the state of equilibrium. And we have a device like this one, L-shaped, and spring is attached there, and some bolt and nuts is located here, and it is assembled at this point B. Pivot is rotation free, and weight is add on here, then some distance, some displacement is changed in this direction. If it is go there, then it can be moved this direction. We assume this L shape is almost reached, we assume. Then we can easily solve problem. When you introduce so-called free body diagram like this one, external force and imaginary force is acting here, F this direction, and at this point, pivot point, we have vertical and horizontal one, and there is no rotational constraint, rotational force, moment. Okay, now let's consider about pitch. How many revolution we require, and movement delta is divided by pitch, then we can calculate revolution. Okay, Hooke's law, here P is confusing. Let's say Fs F equal K delta, that's Hooke's law, and we would like to know this F value, and X direction, Y direction, nothing happens, and we apply their moment relationship, and finally we can calculate F value like this one. If we know F, then we can calculate delta. When you know delta, then finally how many revolutions required for placing back to original position. Okay, that's it for example 1. Okay, let's think about example 2. In this example, slightly different from first example. In this example, we introduce some kind of geometrical compatibility. That's very important. Geometrical compatibility. When something is changed its shape and geometrically it should be fit. That's very important constraint for calculating sigma and epsilon, strain and stress. Okay, here in this example, we would like to think of a system. This system. Okay, upper part, the shaded area A, B, C. This one is rigid. It is assembled on the top of BD. Okay, BD. At this point, D point is firmly fixed to the bottom, to the ceiling. Okay, we assume this component is not moved, it's not rotated. Just it's moving, going up and down. Maybe later on, slight change in this direction, but at this moment we neglect it because it's a bit complicated. Of course, later on, we can think of some kind of buckling problems, but at this stage, we assume B point is going up and down. It changes its distance. Vertical direction is changed. Okay, we have another assembly here. At this C point, some pin joint, there is some component which is connecting to at this point E. Okay, and we can give some force here, some force here. Of course, this component BD and CE, this component, both are elastic. We assume it's elastic. Of course, the shaded one is not elastic. It's rigid. ABC is rigid. We assume rigid. Okay, in this case, some characteristics of materials, Young's modulus or modulus of elasticity is given like this one. 205 gigapascal is given, and when you give a force at this point P, then it goes down there, and maximum allowable displacement at this point A is 1 millimeter. That's the constraint. Then what's the maximum value of external force P? That's our question. We would like to find the maximum value of Pmax when constraint is given like this one. In the mechanics of materials problems, there are so many similar problems because there is some limitation of movement or limitation of change of its displacement in many machines or mechanical elements. Then maximum allowable displacement is like this one. Then we would like to find the maximum value of external force. That's frequently we can meet this sort of problems. Okay, let's move to our problem again. In order to solve this problem, at first we must think of free body diagram for it. When you think of isolation of upper part is like this one, and external force is given like this one, and some forces CE is like this one, and at this point we do not consider any rotational constraint. That's why it's just going up and down. We assume it doesn't move in lateral direction, horizontal direction. That's why we do not introduce any force here. And at this point, vertical and horizontal one we consider at the same time inside. But when you calculate it, this horizontal one is automatically 0 because there is no reactional force like this one. Okay, that's the free body diagram. Okay. Next one. When external force is acting like this one, then maybe finally how we can change its total shape, total device structure. ABC line is in the one line, horizontal line, like this one, ABC. When external force is acted like this one, A is going down there, and some kind of contraction can be happened like this one, and definitely at this point, CE, this component, this element is getting longer. Okay. We can think of this kind of change and change like here, and it happens very systematically. That's the geometrical compatibility. There is some relationship like this one, what does that mean? When you give some forces like this one externally, then the force is automatically distributed to this component and that component, and automatically makes getting longer and getting shorter. Automatically distributed. That's the behind consideration. Okay, that's the geometrical compatibility. Okay, now let's consider about moment and force equilibrium. At first, let's think about force equilibrium, and upper part is positive sigma Fy. Let's say this one, y direction and x direction, Fy, and minus B and minus positive F BD, and minus FCE, Okay, that's the force equilibrium. This one is 0, because it is in the state of equilibrium. Next, let's consider about moment, sigma Fm moment. Let's say this point, because it looks very complicated at this point. Then you can select any point, this point or this point, but I selected this one, B. Okay, P is moving this direction, and counterclockwise P is divided by 450, and C is minus direction, clockwise direction, and FCE equal multiplied by 225 millimeter, then equals 0. Okay, now we can find FCE is expressed in terms of P FCE, and FBD, we know FCE, then we calculate FBD as well. We've calculated this one. That's the force equilibrium, and that's the moment equilibrium, like this one. Next, let's think about geometrical compatibility. Geometrical compatibility comes from this one. Okay, when you consider this one, delta A, and this distance is C, delta CE, same as this one, delta CE. Okay, this one is also delta C, and when you think of this triangle, okay, this triangle, okay, this triangle, we can derive relationship, similarity relationship. Based on similarity relationship, we can calculate something. Okay, based on similarity relationship in triangle, then this distance delta CE plus delta A to distance delta CE plus delta BD, this distance is, and total distance 450 plus 225, and here 225. Okay, we derived another relationship. We derived, when you watch this one, we have many new things, new variables, delta CE 1, delta A, and delta BD. We have this one. Okay, next equation, so-called sigma equals epsilon relationship. We can do that. And if you think of elongation, when you think of elongation is normally give P delta E A. P delta E A. Elongation is normally PL over EA. PL over EA delta. PL over EA. Okay, now calculate delta CE. E, let's assume E is the same as 205 gigapascal. CE, and cross-sectional area, the same, of course, ACE, and P, let's consider C, consider in this case, P, not P, sorry, FCE, let's say FC, and this distance, C is case 600 millimeter. One equation. And we can calculate, we know this value and A value, F we've already calculated there, and of course it is expressed in P, calculate there, and finally we know delta C. Next one, delta A equals what? Delta A equals same. Delta A, sorry, not delta A, delta B, delta BD, because we do not have any relationship here. Let's say instead of A, let's say delta BD, delta BD. In the case of delta BD, E, BD, EA, F, and distance is this length is given 600 meter, 600 minus 120. Okay, FBD, ABD. Okay, we know this one, and A, cross-section area is given, and we know this value here. Then finally delta BD also we can calculate. Okay, we can calculate delta BD, and we can calculate delta CE, we know that. Then finally we can calculate this value, delta A. Okay, we know delta A is some coefficient is multiplied by P. Okay, this one is what? 1 millimeter, 1.0 millimeter. Then finally we can get P value. Okay, in this example, we would like to know maximum allowable forces which is acting on there, and some modulus of elasticity data and is given, and of course ABC, this one is rigid, and constraint externally external movement. This movement at this point A is limited 1. Okay, we would like to know P max. At first we applied force and moment equilibrium. Okay, next step, geometrical compatibility relationship, and thirdly this relationship, delta equals PL over EA. Okay, and finally we can get this relationship, this kind of formula, and we can get maximum allowable P can be calculated. Okay, that's for example 2. It's slightly different. We have two elements in the system. We have two elements. One element is located like this one, and it is connected at this point B, and it is mounted B. This horizontal one is mounted on the top of the base, and force is acting here P2 and here P1. Okay, all the data, the length L1, this length, and another length, this A and B, is given like this one. And here modulus of elasticity E is given, or the modulus of elasticity, or Young's modulus is given. And we would like to know at this position what's the displacement of C at this point when forces are acting like this one, P1 and P2. Okay, it is elastic A, B, C. This vertical component is elastic. Then we would like to know what's the change in vertical direction. That's our question. At first, let's think about free body diagram for this component, and vertical horizontal component be this component is like this one, and P2 is given like this one, P2 is given like this one. Of course, we can think of vertical direction, vertical reaction force, and at this point it is going up, then that's why we can think of downward. We didn't consider the horizontal one because it doesn't make any sense at this point. When you separate left side vertical one, definitely you have RA value, and P1 is given, right? Okay, we assume P3 and P3, we introduced P3 here, but in other direction we drew this kind of P3. Okay, that's the free body diagram. Okay, now let's think about step by step. First, at first, it's very important to find P3 value. In order to that, let's apply the force relationship. Sigma Fy, let's say, equals 0. Let's think about upper direction is positive. And on the left side, P3, this one is minus value, and plus RD minus P2. Okay, this one is equal to 0. And next moment D point. At this point, let's assume 0. and P3, this one is considered this distance A, and at this point 0, and right side is clockwise direction, is different, that's why minus. P2 is multiplied by this distance B, this one is 0. P2 is given, P2 value, this one is given, and we can calculate P3. We know P2 and P3, then we can find RD is known. Okay, everything is okay. Okay, let's move to this point. Think about this one. When you think about this component, based on free body diagram, let's say this one is positive, and positive, let's think of Fy equals 0, let's say, minus Ra plus P3, and minus P1. Is it correct? Okay. Fy direction, same. Okay, we know P3. P1 is given, right? And P3 is of we've already calculated. Then finally we know RA value. Okay. We know RA value. Then finally we would like to know what's the change over here and top of this point, delta C. Okay, at first let's think about this component, AB component. Let's say this point, regardless of this kind of position, P3 is located there, and when you cut here, this point, when you draw free body diagram again, then what's happening at this point? Same value to RA value is acting downward. When you cut here, then when you draw free body diagram again, at this point, at this section, RA is the same. What does that mean? In this range, AB range, acting force is RA really. That's why delta AB is what? EA over distance L, this length is L1, RA, distance is L1. Of course, cross section is A1. We know this value, RA, L1 is given, A1 is given, then we can calculate delta AB. Next, same principle is applied there. When you cut here, when you draw free body diagram again, definitely it's P1. That's why delta BC, which is acting on there, delta BC, which is acting there, this position there, delta BC equals what? Delta BC equals let's assume modulus of elasticity is the same, and length is L2, let's say L2, and acting force is what? P1, and length is L2, sorry, not here, L2, let's say it's changed to A2, EA A2. Okay, then it is under compression. It is under AB is under compression. This one is minus value, this one is positive value. Delta, that's why final delta C equals delta BC minus delta AB. This value is delta C value. Okay, I'll explain. I'll summarize this. I would like to summarize this problem again. This problem is like this one. This problem is like this one. When you have a structure which is attached to here, A point and the D point, and when you push, when you give some forces P2 here and P1 there, and finally we would like to know delta C value, change of its position or displacement. When forces are acting like this one, some kind of elastic deformation can be happened. When something elastic deformation has happened, then this kind of one, AEPL. When you think of P and some elongation delta has happened, cross-section area is A, length is L. Then the relationship, this relationship can be applied, delta. In order to that, we would like to know the values inside here as well, and finally apply this relationship there, and we can calculate delta C value. Okay, that's the second example.